Last year we talked about interest. We talked about simple interest last year, which is when you have interest earned or interest paid and you only get that one time. Compound interest is going to be exactly what it sounds like, where it's going to build on itself, either through a credit card that you don't pay the balance and you get charged that interest as a fee and your balance goes up, or as you pay the card down, you get charged interest on what's left and it may not be as much. So what we're going to look at today is how we can write an exponential function for compound interest. So Madison received $10,000 a gift when she was graduating from college. She deposits the money into an account that pays 5% interest annually. Keep in mind that your rate, which is your percent, we're going to change it to a decimal always when we're working. And then this, we call this our principal. That is our initial amount. So we're going to see if we can't discover what that equation is going to look like. To find the total amount of money in her account after the first year, she must add the interest earned. The interest earned is the one that is a good thing. It's when you keep money in the bank and they pay you like a bonus, that interest for keeping your money there. In the first year, it's the initial deposit. Calculate the interest earned for the first year by multiplying the amount of Madison's deposit, which was $10,000, by the interest rate. And again, you're going to have to change this to a decimal. So we're going to go back to, we learned that in 6th grade, so times 0.05. Feel free to use your calculator. You can use that free graphing calculator app, or if you wanted to just use a regular calculator, you can do that as well. So here is my calculator. I'm going to say 10,000 times 0.05, and we get interest is $500. Okay, so that's the 5% interest at a bank is going to be a very high interest rate. So this is not very real to life, but for our example, that'll work. So including the interest, how much money did she have at the end of the first year? So we're going to have to take that 10,000 plus the interest of 5,000, and we get, she now has 10,500. So she wants to record the amount of money she will have in her account at the end of each year. So what we did here was we said this times 0.05, and essentially we added back in that original amount. So what I want you to think about when we do this, so here's our new amount. We're going to have to say that times 0.05, and we're going to add in what she originally had. So when we go to our calculator, I decided to close. You can say, all right, 10,500 times 0.05 plus 10,500. So now she has 11,025. That's where this came from. Well, I was discussing with a student classmate who was working on this. There's got to be an easier way. I mean, do we really want to say 1125 times 0.05 plus 11,025? Well, we can. You know, we can say plus 11,025 times 0.05. Do we really want to do that for this whole table, though? Because now you can see that the numbers are going to get a little bit ugly. So I want you to think about percentage-wise these values. So we go back to our original. This 500 was this 5%. The 10,000 percent-wise is 100% of what she invested. And we added those together. So really, this 10,500 is representing 105% of her investment. If we go through and we change 105 to a decimal, we get 1.05. So I can easily go through on my calculator, and instead of saying down here 10,000 times 0.05 plus 10,000, could I just say 10,000 times 1.05? And it's already added it back in there. we could then say times 1.05. There's my 1125. I can do that times 1.05. 11,576 times 1.05, because we're just multiplying this by 0.05, which we see there, and adding that extra 100, which we got. So instead of multiplying and then adding, we added it together, our percentages, and now we're multiplying by our total. So we can say 12, 155, and 6 cents. And you're just going to go through, and you're just going to keep doing this. We have 12, 762, we can round that to 82. And that's going to be a lot easier method to fill in a table than saying times 0.05 plus the original. So we can call this 13,496, and we're just going to keep going. Times 14,774.55 times 15,513.28, and one more time. So at the end of 10 years, she has $16,288.95. So essentially, she's earned interest of $6,288.95. So keep in mind, all we're doing, we're adding that original piece in, which is this one, because that's 100%, times that 5%. So we can turn the page. Again, we're only going to go through number 13 on the notes thing. We're going to finish the rest of the notes in class tomorrow. So the amount of money in the account increases by a constant growth factor each year. What did we multiply by? Well, we multiplied by 1.05 because that was our 100% plus our 5%. How's the interest rate on her account related to the constant factor? Well, 5% is 0.05 and 1.05, right? It's the decimal portion. The decimal. Instead of calculating the amount of money in the account after each year, write an expression for the amount of money using 10,000 and the repeated multiplication of the constant factor. Because that's what we did. We said each time. We didn't even have to put in a number. We just said times 1.05 times 1.05. So for the first year, 10,000 times 1.05, 1.05 to the first. And I said, all right, so if we go back and we look, I did times 1.05 times 1.05. And we know that when we multiply by the same number over and over and over, we can raise that to a power. So in the second year, I had multiplied by 1.05 twice. In the third year, I had multiplied by 1.05 3 times. The fourth year, I did it 4 times. The fifth year, and so on. So this is going to help us write that equation. And if you remember, our exponential equations are such that we have a b to the x power, right? So our a is that 10,000, that principal amount. B is our constant factor of 105, and x in this case is going to be our years. What is the relationship between the year number and the exponential expression? Okay, so right here, what we were talking about. So we can say the year is the exponent. Okay. Write an expression to represent the amount of money in the account at the end of year 8. So now, we said year is x. So in our equation, y equals 10,000 times 1.05. This is my x, so instead of x, we're going to put an 8 here. If t is equal to the number of years, write an expression to represent the amount of money in the account after t years. So, and this is just an expression, so we don't need an equal. So say 10,000. So instead of x, they want us to use, right here, they want us to use t. So 1.05 1.05 to the t power. And then if t is 6, we're going to plug that in, and we're going to use our calculator. And we're going to say, okay, let's say 10,000 times 1.05. Remember, here's your caret to the 6th power. And we get 13,496 cents. Well, let's see. Did we do this correctly? Flip your paper back over. That was your 6. Same exact answer. Okay. See, for 10, so I'm going to say 10,000, 1.05 to the 10. Again, 10,000. So we're not having to do like a recursive formula where we're multiplying by 1.05 over and over and over like we did up here. Now this is almost like our explicit formula, but we're starting at 0. So times 1.05 to the 10th. So we get 16,288 and 95 cents. Which again, if you go back, was number 10 here. Function m of t, where m of t is the total amount of money asked here. So now they want us to write an actual equation. So instead of y, they want us to use m of t, the amount of money, is equal to 10,000 times 1.05 to the t, is our equation. So now we can graph that. And you have a couple of options here. You can use the table to graph it, or you can go to your calculator. We talked about this the other night. You can go to equations. If you still have an equation there, we're just going to clear it out and save. Move it over here so there's not such a glare. And we can easily say 10,000 times 1.05 to the x power. We're going to save it. We're going to graph it. Now we can't see it. So normally on our graphing calculator, we would change the window. We have to use some buttons. We know it's not going to start until 10,000. So we're going to have to come over here. There's 1,000. If you just pinch it, it's going to zoom in for you. So you can move it down. But here you can see now this is really close because of our scale. Here's the 30,000, but if you look at our Y scale, or our X scale, that's part of the reason it looks so funky. So in this case, it might be easier just to use our table, but we can go to a table here so we don't have to flip back and forth. All right. So 0 is 10,000. 1050. Now look, or 10,500. We're counting by 5,000. So this is going by 2,500s, right? So I'm going to skip to 2. 11 is just a little bit higher. Kind of in the middle. We can go to 4 is 12. Okay, well this is 12,500. So 4 and 5 are kind of close there. I'm going to try to go to 4.5. 8 is 14, 7, 7. So this is going to be 17,500. 14 is going to be pretty close to this 1,500. Now it almost looks linear because of our scale. I'm going to jump down here to 12. It's about 18. So that would be about here. So it doesn't really look exponential because it's increasing by such a small amount. Okay, however it is. Describe the function as linear or nonlinear. So of course it is nonlinear.